Hello, I'm Xupeng from Chile's Academy of Sciences. Today, I'm going to introduce our research work, Cooper testing the binding code of scripting languages with cooperative mutation. It's a joint work with researchers from Qianxin and Penn State University. As we all know, scripting language is very useful and powerful. It's easy to learn and develop. Nowadays, scripting languages are integrated into document processing programs. For example, JavaScript code is integrated into PDF and HTML. VBA code is integrated into Office document. In these programs, embedded script code are usually used to manipulate the content elements of a document. Vulnerabilities in these embedded scripting languages are very dangerous. Attackers can exploit vulnerabilities in these programs to execute abuse code and take control of the system. And every year, many vulnerabilities are discovered in a better scripting system. So it's essential for us to design an effective method to find bugs in embedded script code. First of all, let's look into the interface of document processing programs. The input contains two parts. Native objects represent figures, texts, and even annotations. Script code contains scripting languages like JavaScript code here. The program also has two components to process inputs. They have native code to handle native objects and use language interpreter to execute script code. To connect two different components, these programs usually have a binding layer to do translation. However, the binding layer is too complicated to be 100% correct, and bugs are inevitable. Previous work, like FiveCardinal, only focuses on mutating the script code without any mutation in native objects, which may miss the complicated bugs. We take a vulnerability discovered by Cooper to demonstrate our concept. It's a heap overflow in Adobe Acrobat. Attackers can use this vulnerability to run abuse code remotely. It's so severe that we were awarded with $2,500 bounty for this particular vulnerability, and it had been patched by Adobe before our paper submission. Then let's see how to trigger this vulnerability. First of all, in native objects, we must insert one extra element into find array. Then in script code, we must utilize JavaScript code to change the zoom type of the document to RefW. So as you can see, to trigger this vulnerability, we must mutate both native objects and the script code. And the traditional one-dimension mutation further cannot find this sort of vulnerability. Inspired by this vulnerability, we wanted to design a new solution to discover this sort of vulnerabilities related to both native objects and script code. Our solution is cooperative mutation. It's very simple. We mutate both native objects and script code in cooperative manner. So we come to the problem, how to achieve cooperative mutation. First of all, we need to infer the relationship between native objects and the script code, and then use the inferred relationship to get mutation in both sides. Specifically, if a script API has a potential connection with some objects in a document, we will assign these objects a high priority for mutation. Otherwise, we just randomly choose some objects for mutation. While our method is simple, there are also several challenges to be solved. The first challenge is how to infer the relationship between native objects and script code. Once we have the relationship, we need to solve the second challenge, how to use the inferred relationship to get mutation. However, when we solve these two challenges, we can encounter a new problem. There are so many native objects. That means we will have a huge search space for inferring relationship and getting mutation. It's not doable. To solve this problem, we need to reduce the search space. So how to reduce the search space? We plan to categorize all native objects into different classes according to their semantic feature. So let's come to our challenge 0. How to cluster relative objects into semantically similar classes. The next figure presents an overview of our solution. It has 3 components. The first component is object clustering. It clusters a large number of relative objects into a small number of object classes according to their semantic feature. Once we have object classes, we need to infer the relationship between object classes and the scripting API. This is the purpose of our second component, the relationship inference. This component uses as a statistical method to infer the relationship. Finally, we come to the third component, relationship-guided mutation. In this component, we use the inference relationship to guide mutation. Then I will show all components in detail. The first part of our solution is object clustering. An object usually consists of some attributes. Each attribute is a pair of name and object. Through our observation, the name of an object usually carries some semantic information. So in the first step, we cluster relative objects with their names. It's very simple. We just put objects with different needed names in different categories. However, in some corner cases, clustering objects by their names may not be correct. To get a fine-grained object classes, we split and merge object classes with attribute similarity. Specifically, we use that formula to calculate the similarity between object classes. If the similarity is less than the threshold value, we split big classes into small classes we split a big class into several small ones. If the similarity is greater than a threshold value, we merge these small classes into a bigger one. Through these 2 steps, we finally get a set of fine-grained object classes. The second part of our solution is relationship inference. We take 2 steps to infer the relationship. In the first step, we do execution logging for all samples and divide them into 2 sets, success set and failure set. Specifically, we prepare testing code and insert the testing code into the orange sample, and we use the application to open a new sample. If the testing code successfully finds assignment-related objects, we put the orange sample into the success set. Otherwise, if the testing code cannot find the related elements or produce error, we put the orange sample into failure set. So through the first step, we have divided all samples into success set and failure set. After we divided all samples into success set and failure set, we use statistical method to infer the relationship between object classes and scripting API, and we get a relation map. As you can see from the map, the success rate is the percentage of samples that contain this class of objects in the success set. The failure rate is the same percentage in failure set. The difference is the difference between object classes and between success rate and failure rate. We think the different values represent the strength of the relationship between object classes and scripting API. In the second part of our solution, we have got the relation map between object classes and scripting API. In this part, we will utilize the relation map to guide mutation. First of all, we determine a target API group. Then we take a traditional method to generate a script code. For relative objects, we get a set sample and select objects in this sample for mutation. Specifically, we refer to the relation map and design an algorithm to calculate the mutation probability for each object in the set sample. In general, the mutation probability is positively correlated with the strength of the relationship. Then we select some objects with mutation probability and mutate selected objects in 3 mutation strategies. Finally, we synthesize the mutated sample and script code together and produce a final input. So let's walk of our solution. For implementation, we developed the Cooper in 4,300 lines of Python code, and Cooper has utilized some open source library. In particular, it uses PyPDF2 Python library to pass PDF format, and uses zip file and XML Python library to pass Word format. For script generation, we utilize Domato and improve it with block level template. Cooper currently supports two formats, PDF and Word. It's notable that Cooper is extensible and portable. You can easily add some new features to Cooper and can also apply Cooper to other document formats with limited manual efforts. Then I'm going to talk about Cooper's evaluation. We apply Cooper to real-world programs to find bugs, and we compare the capabilities of bug finding and edge finding in different configurations and tools. We apply Cooper to three real-world programs: Adobe Acrobat, FoxReader, and Microsoft Word. In 4 months, we totally found 134 progress unload bugs, got 33 CVE numbers, and 59 bugs have been fixed. We were totally awarded with $22,000 bounty, and all these vulnerabilities are related to 90 API in 11 objects. We applied different configurations on Adobe Acrobat and recorded their bug finding history in 1 week. As you can see from this figure, Cooper 4 found 18 bugs in 1 week, which is the most among all configurations. This result proves our concept that cooperative mutation is essential in bug finding in binding code. We also do the experiments on FoxReader, and the results is similar to Adobe Acrobat. Cooper 4 always found the most bug. To test the edge finding ability, we apply all configurations to Adobe Acrobat and record the edge finding history in 1 week. We record both scripts coverage and native coverage. As you can see from these two figures, Cooper 4 can find the most in both types of coverage. We also do the edge finding experiments on FoxReader and Microsoft Word. Their results is very similar to Adobe Acrobat. Cooper 4 always found the most coverage. Their results can also be a proof of our concept. In conclusion, we propose cooperative mutation to test the binding code and the binding code of scripting languages. Our system, Cooper, found 134 bugs in Adobe Acrobat, FoxReader, and Microsoft Word, and received 33 CVE numbers and $22,000 bounty. And Cooper is now open sourced at this website. Thanks for listening. I'm ready for questions.